All right, any questions before we continue with graphics? All right. We'll do graphics today, probably also Thursday, and then we'll be done with it, and you'll play around in the lab doing some of these things. So anyway, let's go where we were. Went over a little bit of the history, and we got to this point where we're going to start looking at data that you'll look at quite a bit during this term. This is a study relatively early in the history of antiretroviral treatments for HIV at San Francisco General Hospital. So this was collected, as you can see, from 96 to 2000. There's about 500 people in the data set that you have access to. And it's clinical data, not really an organized follow-up. I mean, it is a follow-up study, but it's very messy in the sense that people come in depending on when they perhaps have an illness or when they make an appointment, and you have lots of variability in the times they come in and the amount they come in. So some patients come in very, very frequently. That can be kind of a bias, right? Because if you're not careful about how you analyze the data and weight individual observations, some people who come in quite a bit could overly weight your associations, and they tend to be different kinds of patients if you look at them. And you're welcome, the data is up there. You can play around and see, but often people who come in quite a bit are sicker than people who come in less often. But it's not perfect. There can be other factors, socioeconomic factors and things like that as well, and you can be too sick to come in. And this was a time when a lot of people were still dying from HIV, and they were trying to figure out how well these antiretrovirals would work, and they were looking at sort of the variation in how people responded to them. This is a lot better understood today, and there's a lot of other kinds of drugs, but some of the same sort of patterns that you see here apply. I guess with the difference being you don't get as many people who come in very, very sick. You tend to get them earlier because of greater testing. So as you can see, the number of variations, varied from, forget it. You're never going to get used to this thing. It's just wasting your time. Anyway, here's a plot of the data. So this gives you sort of absurd idea of the challenge of longitudinal data. This really is a plot of all the data showing the viral load and the CD4 count. One of them is in red and one of them is in black, and it doesn't really matter, as you can see. Obviously, you can't, in many studies, there may be situations where you can just plot the data, raw data. I suppose in very small longitudinal studies, some of which we have, that we'll look at, it's not unwieldy just to plot what the response over time or the two responses over time together of all the individuals. But when you get any substantial size, you have to start thinking cleverly about how you're going to plot them and sort of show the variation, the patterns. And I'm going to give some ideas today, and some of these other chapters I recommended reading have other ideas for how to explore longitudinal data. Some of them have to do with just exploring what the patterns look like. Some of them have to do with processing the data, so when you plot it, it's addressing a specific question, like how does the change in one thing affect the change in the other. We'll do a little of both of those in these next couple chapters. So again, I'm relying heavily on Stata to teach this. Those of you who are R programmers will be able to see the logic in the Stata code, and it won't be much of a challenge, I don't think, to redo it in R, and I can certainly help with that. But Stata is very nice for plotting longitudinal data. Has lots of very nice lower level functions that are just used to plot in general, and some higher levels that are specifically for longitudinal data, which we'll get to. But anyway, obviously you have to do something, because you can't simply just plot the data and hope to see a pattern. there are specific plots for there are types of longitudinal data where people tend to make certain plots that make a lot of sense. When we talk, if we get to survival analysis, there are plots one almost always makes about survival over time called Kaplan-Meier curves. So, I mean, there are sort of standard plots for certain kinds of longitudinal data. And a time series is another one. If you have single time series, that's quite straightforward. You plot the time series over time to explore it, because that's essentially what makes time series data unique in this sense compared to these other things we're looking at. Is you have one unit densely measured over time, and so you don't have 500 units that you're trying to distinguish their different types of patterns. We're going to concentrate on this data. You'll do some other data in the lab. And I think I'm going to have you work out of Weiss, the book that's posted on the BSpace. He has a nice web page, which I'll also put there, that has all his data sets in there. And he also has SAS code for everything he does in that book. So for those that want some SAS support, it's very nice. He's on a web page. He's got all the SAS code used to generate output in the book. But anyway, we'll do that. Okay, so yeah, this is just obvious stuff, except for the last one, perhaps. I mean, there will be graphs we make that address particular questions. There's two stages. I mean, typically people go through a data analysis, and it was sort of pointed out in that graph of sort of that original kind of longitudinal data about Christianings in England after the time of Henry VIII. That you plot it, one, to see patterns that you may not have thought of, but you also plot it to look at mistakes. That's sort of crucial with longitudinal data. You know, something we're not going to go over here systematically in this course is that if you're getting your own data set and for the first time, and it involves lots of records of individuals over time, inevitably there's errors. I've almost never been in a study where there wasn't entry errors on variables. So one of the first fundamental things to do is just plot the distributions of the data, plot individuals over time, take subsets of them if you can't look at all of them, and you're just looking for things that just don't match, that look peculiar, because it's hard to see it when you're typed in a table. It's hard for me. It's much easier to see it, of course, in a graph. And so oftentimes the graphs are systematic ways of doing quality control, and longitudinal data is particularly prone to errors. I would say that's even more true in clinical settings that are not highly regulated by some sort of clinical trial they're doing. They're observational studies, and nurses and doctors are busy, and they tend to copy down things wrong quite a bit. So that's sort of the most fundamental thing to do, is to look at the data to make sure it's all right, to make sure there's nothing, you're looking for big errors, obviously, not subtle ones at the second decimal place, but at least you won't have calamities like making a whole study conclusions based on a misinputted number. The other thing, of course, is just to find patterns, which is a reasonable thing to do if you're doing particularly exploratory analysis. You don't really have well-defined hypotheses. You want to look at the kinds of trends over time, and you want a systematic way of doing that. That's you have to get, you're a little bit in danger of starting to so-called data dredge if you're finding patterns and then using those patterns to create models and then making inferences off those models. Well, there's always an issue with that unless you have if you want to do that kind of thing and you want to be absolutely safe, you always have a training set where you break your data up in a training set and you have a testing set. People never want to do this because, of course, that's cutting your power in half to detect things. But in that case, at least you can do anything you want on the training set. And then when you evaluate it on the test set, it'll be like doing a fresh study. So you're getting a true confirmation of these things that you find. I really recommend it as a strategy if you're really doing exploratory work, because it's really, really easy for people to find patterns that don't exist. It's people demonstrate this fact all the time by giving random data to a class of 40, and using a little guile, we'll say things like, I know there's an interesting pattern here. The student gets 10 extra points if they find the pattern, and sure enough, there's like 15 really amazing associations that people find by doing lots of plots. It's just like staring at what did I do as a kid? Stucco ceiling. My parents said, acoustic ceiling. So, that dates me. That was a big thing in the 70s in track homes. Everybody had acoustic ceiling, and you could stare up at the ceiling. You could create incredible imagery that came. I could never draw anything, but I could imagine like the most perfect rhinoceros and Farrah Fawcett when I was a little older. Anyway, you can create patterns quite easily if you're looking long enough at data. So if you really doing exploratory analysis, you really have to be careful you're not creating patterns that don't exist. That's why if it's really getting in there, trying different stuff, and then trying to verify the model, you need to have a sort of training data set. There are, I will let you know, there is methods being developed that allow you to do this by breaking up the data in a bunch of bits and doing that training on different data sets and then testing it on all the left out sets where your training sets overlap, but your validation sets are all unique. And you can still derive good inference. That's hopefully will be software available in 5 years or something like that. But for now, practically, you're talking about cutting it up in some 2 slices and doing it in a very blunt way. Okay, this is just a portion of the kind of data set we're going to look at. Again, it's the HIV data set. There are, got to get used to not doing that. Okay, middle. There are a row of IDs. Again, this is long format, so every observation has a different row, and then you have a variable that tells you what unit it is. This is very standard, necessary when we get to doing these higher level regression techniques. Typically, the time things are measured, and then you've got, in this case, our viral load and our CD4 count. And we'll be thinking of our CD4 or viral load as sort of our explanatory variable and time as well, and CD4 count as our outcome. That's the way it was thought of at the time, and it still makes, of course, sense because CD4 count is the result of viral load attacking the immune system. You get a reduction of CD4 count. And again, the data, just to reemphasize this point, which I'll make several times, the data just comes in as it comes in. This is cleaned and looks kind of nice. I mean, it's a big mess to go from what it looked like on charts and things to what it looks like now. But if I want to do things like look at lags, like I want to look at what is viral load at one time here, let's say, and its impact on CD4 count later, because I don't necessarily expect that the cause and effect occurs quickly. There may be a delay, and there in fact is a delay between these two. I'm going to have to shift the data so I get future CD4 counts associated with past viral loads. There's all kinds of embedded data processing that's necessary depending on the kind of questions you ask and how you look at the data. Okay, I'm just going to make the same absurd plot. This is a really useful command for just getting a plot of the data versus time. So xt line, it just connects the dots for observations made on the same unit, and of course you have to give it the ID so it knows to start a new plot for a new ID. You give it the time variable, so whatever you want to plot it against. Doesn't have to be time. Could be explanatory variable. It doesn't know that it's time, so you can put what you want there. I'm doing time. Overlay just means I want all of them overlaid, and then you can put, of course, with stat graphing commands, you can put all kinds of other things to change the aesthetics of the plot. So it's quite flexible, and I've barely done anything in this case, just the bare minimum. Again, This now is just CD4 count. As the other one was viral load and CD4 count in the same plot. This is CD4 count. You can see it's just another point that's kind of absurd. I can't really see. You do see some things. I mean, you do see a big pile of people down here. I can't really see where their trajectories are going, but there does seem to be a lot of people that are kind of flat right there. And we'll see this later when we start doing more sophisticated ways of dividing up the data. But so I have a lot of people that sort of start low. This is the time zero in this case is when they are put on HAART, highly active antiretroviral therapy. Is that right? Yeah, I think that's right. So this is these viral drugs that revolutionized survival with AIDS. But you can see at the time, people who often start low don't really improve their CD4 count. Some of them you can't see, but will be stopping halfway into the study because they pass away because they're never able to overcome the disease, and they die of the various sequelae associated with HIV. And then some people start high and go down. Most people actually do kind of go up. So it was, we know it works, and these were early drugs. They're much better, and many more of them now. I think it's AZT was the one used at the time. But anyway, not a great plot, but it does give you some idea of what's going on. Okay, so we're going to now, again, this is totally ad hoc. I'm going to give you some ideas about how to process data to try to see the patterns more easily for yourself and to communicate to your audience. And we'll just go over various ways of doing it. And again, it doesn't mean that this is exhaustive. I'm sure many of you have the ability to come up with more clever plots. But anyway, a lot of this is also the fact that I put some code there that shows you how you might actually do this in practice, and I'll have you do it in practice. For those that are using a different programming language than Stata, it's really good to try to figure out how to do it yourself. These aren't huge challenges, but it takes a little bit of cleverness. I will say that also the code I give is not unique. You could do this in make the same plot in many different ways of getting to the same end. I tend to code in Stata in a really sort of an elegant and exhaustive way so you can sort of see every step. There are higher level commands that often will do these things much easier. But I think one of the virtues of this chapter and a few others is just to sort of get some familiarity with what you can do with Stata, because Stata is really quite powerful. It can do all kinds of things. It's its own programming language, as well as a very good applied stat thing. So anyway, we'll start by just taking a random sample. That's kind of the obvious first step one could take. And then hopefully that will you'll get a representative sample, and you'll be able to see enough of the data that you can see sort of the characteristic patterns. And then we'll talk about taking more systematic approaches later, and then we'll talk about how to process the data so you can see patterns that aren't affected so much by random noise. Both CD4 and viral load measurements are very noisy measurements, and so some of what you see may be real, ups and downs, some of it may be actual, just the fact that the measurement itself, particularly at the time, wasn't very accurate, or precise, I should say. Or, oh God, I always get that messed up. What is accurate? Precision is one's bias and one's variance. I know what they are, but I don't know where it goes to what. So hopefully you do. All right, so I won't test you on it. How about that? No. A lot of these things require you to sort stuff. Okay, so in Stata, if you want to plot stuff and you don't sort it, you'll find, you'll get plots that look like this. It'll go here and then back here, and they can be kind of cool, but they just are chaos. So you sort the data. So in this case, I'm sorting time within ID, and I'm going to do this for reasons that you'll see. Is I'm selecting a random selection of not observations. I'm taking a random selection of individuals. Okay, so individuals are represented by different rows. So if what you sort of want to do is take that first row of each individual and draw randomly from that first row, and if you draw that row, you want to take all the other rows with it. You see that? If I took a random observation of rows, then people who, first of all, I wouldn't get the pattern within a person because I'd only get some of the observations. And secondly, people with more observations would be more likely to be sampled, obviously. But anyway, the first one makes it silly to do it that way anyway. So what I do is I sort time with an ID. So when I relook at the data, if I looked at it, and you'll do it yourself, I'd have what I saw actually back here. No, I don't want that thing. Okay. The data was already in that form originally. Yeah. You can see that time is sorted within each ID. But anyway, to make sure, we do it again. Oh, and just so you don't get worried, I'm not going to go over every line of code in the lecture, okay? Because I know you'll flee if I do that. So we'll just go over some things to get you the logic of how you do this, and then you can start going off on your own and doing it. So anyway, what I do is I generate a random number, various ways of generating a random number in Stata, and I want to take a random draw. There's other ways of subsetting. There's a sample command, and I could do it by making a data set of just IDs. So what I could do is delete any observations that are beyond the first row, collect just the unique IDs, randomly sample those, save that data set, go back to the original one, merge it with that one, and then only take those ones that I get a successful merge, right? That would be another way to do this. You can do a lot of fancy things by doing merging with Stata. You can, in terms of getting subsets of the data you want to plot, because there are subsetting functions, like sample is a function. I think it's called sample in Stata that will do that. I'm going to do it without having to change the data set, because I like not to have to read in new data sets and alter them as much as possible. I like to do everything by indexing. Like I try to make a new variable which says plot if this thing is equal to this, so I can just keep the original data set and I don't have to reread everything in again every time. So that's how I'm doing it. And this little internal command, for those not used to it, Stata has its own internal variables. You don't see them when you get in and you list your data set, but they're behind the scenes, and the underscore n is the row number. That's all it is. But if I do it it's the row number relative to the ID. So underscore n equals to 1 is the first row, underscore n is the second row, and in this case, it's that for each ID. So it starts recounting as I go to the second ID, 1, 2, 3, up to the number of rows for that ID. So anyway, I'm only generating a random number for the first row of each ID. I'm not doing it for every row because, again, I want to use that to sample people. And then I'm going to rank them. Now that ranking is random too. So I'm ranking the IDs. And then I'm just going to, I now need to make sure that every observation in that ID has that rank in it. And this is just a trick to do that. So it just fills in. Because originally I'm going to do this, I'm going to have a rank, I'm going to have ID and a rank. And I'll have, 1, and maybe it'll be rank 10. And then 1, it'll be blank, blank, blank. And then I'll get to 2, and that may be 4, blank, blank, blank. I'm just filling these in. I'm just filling this 10 in here. That's what this thing does down here. So it's just a little trick that does that. Not interesting. It's just making sure when I grab now the top ranks, it's going to grab every observation from those IDs I randomly draw. And then I'm just going to plot some set of them. In this case, I'm going to do 24, which is 5% of the data, roughly. And that just means give me all those ranks that are less than 24. You can do this other ways, and I'll show it to you. I mean, there's lots of little tricks. If this chapter is good for anything, and I hope it's good for something, it's good to go, I think, over the code and try to understand it. I think there's a lot of useful stuff in here. It's not all mine. It's derived from other people's work as well. But anyway, once I do that, I can plot it. I subset it to only that random set of 24 people, and I choose. I hope that will give me a better sense of the variation I see in patterns over time of CD4 count. And sure enough, this seems a lot better. You do get the same kind of gestalt that you do in the previous slide that had them all on, but I can see that there are these really these people that are starting, I mean, really, you're starting with a CD4 count, let's say hundreds here. I mean, that is really, really low. In fact, dangerously, dangerously low. Very easy to get opportunistic infections. And so a group of people who are starting quite sick, there's a lot of, we talked about these kind of cohort effects. There's a lot of, there's people here that are basically at different stages of their disease. They're not, the time zero isn't time of diagnosis or time at which they derive the HIV virus. That's often almost impossible to know. It's the time at which the study started. So you might be getting people that are entering shortly after they got HIV and people that might have had it for years, right? So you're getting this mix of different kinds of people in the data set. These people are obviously have fairly advanced disease because their CD4 counts. None of these are normal CD4 counts, I don't think. Normal is higher than 1,000. But these are quite low. And of course, these are very dangerously low. And you see, what else do you see? Like, what are the kinds of things you start noticing? If I'm trying to model this data and I want to say something about the process of CD4 count over time, just what are the type of things you start to notice here? Just free-flowing.
If you're low, you stay low. If you're high, you
Yeah, that's a really good observation. If you're low, you tend to stay low. So there is some people that tend to go, they look like they go up, but it almost reaches a plateau. So if there is any, I mean, I may be over-interpreting, but if there's any benefit, it seems to be limited. So there's at least at this stage of these drugs during this era in HIV, if you were already really sick, the rebound in your CD4 count for the most part was fairly modest, if it anything, and then eventually, for many of them, it didn't work. And you'll notice this is down to 0, and then it ends. Well, it doesn't end. It ends, could have ended because of censoring, but it very well could have ended because the person died, because you're getting quite a low CD4 count there. And you can see that observation that people that start higher tend to have, more potential to recover this part of their immune system. I'm not an expert in HIV, but they're getting higher CD4 counts as time goes on. There's a general trend above here, thus that you see that people are going up, and a kind of general trend here that they might be a bump, but they're going down. Obviously, lots of variation in these people versus these people. You notice over here, a lot of these models, if you're really worried about the model of the whole distribution, will assume that the residual variance around some, projected mean CD4 count will be equal regardless of the value of your covariate, in this case time. Not going to be true. These people seem a lot more variable, right? And that's probably because higher CD4 counts have higher variability. It's a really common phenomenon in biology that the higher the mean, the higher the variance. That's why people... Did my mic? Oh, back on. Because that captures, that takes your variation and standardizes it by the mean. So you see that, and you see very low variation here. I mean, one reason is you have a bound of 0 here, but there's something else going on. Now, there's exceptions. There are people that go up and down within that group. So great changes and lots of difference in variability. That is no other thing that longitudinal data allows you to look at that maybe a cross-sectional data set wouldn't, is you don't necessarily have to look at the mean of an individual. You can look at the variability as an outcome. That often is quite interesting to say, is there differences in the lability of a subject in different groups, treatment groups. So that's something else you see. The obvious thing that people start at different levels and that they increase at different rates. And there is, censoring and this very different, a lot of these big flat spots here, it's a little misleading. What you would like to, you could put this on the XT line, but you'd like to put little circles where the measurements are. In fact, I should do that next time, because some of these smooth things are connecting dots that are this far away. So that's just misleading. It's not that they're that smooth, it's that they didn't come in between that. This person, my guess is, just comes in a lot. So some of this is just artificial. But again, you start noticing these things, and that's why you add features to your plot. Anyway, that right away, there's a lot that you might start putting in a model if you were trying to model this process by looking at this plot, doing exploratory work. And it gives you just a real sense of the type of people there are in this data set. And anyway, there are other ways, though, that you can do this you want to get a small sample, but you want a representative sample. And so if I get a very small random sample of the set of subjects, I may not capture all the spectrum of patterns that I'd want to get. So you can start trying to sample your data more systematically. And that's what we're going to talk about now. So you want to create some summary of the entire history of the subject, maybe their CD4 count over time, some summary of it, and then rank them by that summary, and then choose in increments. You could do it by the mean. You find the mean CD4 count measured for each individual over the study. You rank them by that mean, and then you take every fifth one, right? So it's a systematic sample of people on the low end of the mean spectrum to the high end. So basically, I'm just going to go over ways of doing, or ideas for doing that. And again, the summary statistic is not an objective thing. That's something that you use to try to capture people related to whatever question you're answering. Mean CD4 count, if you look at that previous plot, looks like a pretty good idea because there tended to be people that were kind of low and people kind of high, and we might want to make sure we get a good representation of all those types of people. And maybe getting a random draw, we don't quite do that. Anyway, you could do this many different ways. You could weight the probability of grabbing a subject based on something if you want to oversample certain people, whatever it is, all quite doable. Yeah, so this is what I just said. So again, we're going to do that same process again. In this case, it's just going to be the mean. This is I'm just here giving you a little refresher on the notation that we had. I'm getting an estimate of the mean, but for each individual. Is that a parameter or is that a random? Is mu I? A good question is, what is mu I? What does that equal to? I'm estimating it here, but what could it be? What experiment would give me mu I? Remember, it's indexed. Think about notation. It's indexed by I, which means it's different for each individual. Exactly. So it's different for each individual. That tells you it's going to be random something, right? Because this is a random sample of individuals. So it's not going to be a parameter, which is a characteristic of the distribution of all individuals. This is a random something. Now, all I'm doing, you can see, despite the irritating notation, is just getting the average of the CD4 counts for each subject. And of course, they differ. The numbers differ. So, I sum them up and I divide by how many observations there are. So that's an estimate of some kind of mean. But what experiment would give me the mean that might be mu I? Yeah. Yeah. Like how repeatedly? What'd you say? I'm sorry.
Well, the more measurements, the better your estimate.
Yeah, I mean, basically, let's say if in theory I could measure every second CD4 count, and again, mu I has to be the experiment has to be defined explicitly over some, repeatable experiment. So I could say for 1,500 days, which is the length of the study, with some exceptions, some people went longer, I measure every day CD4 count for an individual, or every minute, or whatever it happens to be. And then I'm estimating that by the random sample I have. And then, of course, that leads to the question of, okay, so if that's my experiment that gives me this, so this would be the mean, essentially would be the mean under a data set where I had no missing observations. I can think of my true data set as one where I had every person, let's just say every hour I had a CD4 count. And I have a missing data structure. I get a set of measurements made at some kind of intervals, but most of those observations are missing. If I want this to be an unbiased estimate of the thing I really want, what would I have to assume about these j's that I'm getting on the individual? Yeah. Yeah. Yeah.
Timing of the measurements is random.
Yeah. There's just a random set, right? I have a random draw from this almost infinite population of measurements. No, probably not true. But I mean, this is the sort of steps you go through to figure out what this thing is. I mean, it's a reasonable thing we're doing. We don't have to overthink it, but just a good illustration of trying to figure out what is exactly the thing I'm estimating, what are the assumptions by which I'm getting an estimate that is a unbiased estimate of that thing. So if the sampling times are somewhat random sample of the times I could have had, then I get an estimate where in repeated experiments of this type where I put all those observations for the individual in the full data set in a bucket and randomly draw them and get repeated averages, the mean of that thing would be the true one. That is, if I just take everything out of the bucket and average it, right? These are the kinds of experiments you think of your head when you're trying to define what the thing I'm interested in. It's kind of a random parameter in this case. So it's a parameter in some sense because it's defined in the limit of taking an infinite, for instance, an infinite average, but it's not really a parameter because it's indexed by the person and I have a random draw of people in my population. So some people would call it a random parameter. Yeah.
Can I overthink for 1 second?
Sure, go ahead.
Okay, so in this case, there's the issues you brought up earlier that people may come in when you're sicker or whatever. But I mean, for repeatability, I can't think of experiments where the timing of measurements are genuinely random, like more often they're scheduled. Even when you're able to design an experiment, measure people monthly, etc.
Right.
It's still not actually reasonable.
In that case, I could define my random parameter of interest as the average over those regular observations, and then I, in fact, would be not getting an estimate of that thing. It would be the thing, right? It's just a question of what you're interested in and what you're estimating. If those systematic samples cannot be treated, sometimes they can be treated as a random sample, and that.
There's no reason to think that the third Friday of the month
Yeah, or something like that, right? So yeah, that's a good point. Anyway, so what I'm doing here is, for those who haven't done much data,egen is like the gen command. I hate this. I don't know why they came up with the syntax, why they couldn't just say this is equal to that, but you put this gen or egen ahead of it. Egen is just making new variables with these sets of higher level functions, like I can do a mean. I could just do mean over the whole data set, and that means for every line it would just give me the mean over and over again. Or I can do it by some other subunit. In this case, I'm doing it by ID. So I'm ranking by the average CD4, this thing right here, and I'm doing it by ID. So I do that again, and then I'm counting again by ID, and then I'm ranking them, but only among the first observation for person with that CD4 count. I don't want to get duplicates if they have the same mean, and it turns out some people do have the same mean. So if I'm only ranking the unique averages. I mean, again, it's subjective, but it's what I'm doing. And then I'm again filling in. I do these sets of things right here, basically to get equal increments. I want to be able to sample every 24 subjects. So every 20 subjects, I'm going to go down. I'll sample. Once I rank them by their mean, I'll sample the first one, then I'll sample the 21st one, and then I'll sample the 41st one, et cetera, until I get to the end, right? That gives me a systematic sample across the range of means. And that's what all this is. All this stuff is right there without, and there's various ways you can do it. Again, there's probably 20 ways you could do this. I'm just showing you one way. And then I'm plotting it. So again, ranking by the means, and I don't want a random, that makes no sense to take a random sample anymore because I'm trying to do something systematic. I'm lining up these, ranking them and then lining them up. Let's say the mean is 0. Some people are close to 0, and then this next one might be 11 and 24 and 101, etc. 150. So this is their mean, CD4. And then I'm taking this one, and I'm just, let's say I get every 2. I'm just going down and grabbing them. And I do it by creating a variable that says, okay, you're somebody I'm going to take. You're going to ignore because you're not in, 11 I ignore because it's not enough observations away from the previous one. Again, you can do this by using the sampling other ways. And then I look at that thing. So this now gives me sort of a systematic look through the subjects ranked by their mean. You can see that a lot of people are at the low end here, right? So even though I'm going every 20 subjects, I have to get pretty high up in the mean before I start getting subjects that don't have relatively low mean CD4 counts up. And I get these ones at the high. So this is going to be one of the highest mean CD4 counts. And now I like these plots a little better because now I'm not going to get some variation that's just due to the randomness of how I chose. I'm going to get something that really reflects the range of patterns, but I'm defining that selection based on the mean. I could do it on other things as well, of course. And this is one of those other things. This is actually highly, I'm just going to zoom through this. Area under the curve is often used in longitudinal studies to characterize some pattern because area under the curve can represent sort of the accumulated exposure to something. It's used a lot in drug trials where they measure drug levels in a person and they want to get what is the total amount of drug you got in your system, and they take the curve, and of course they measure it at different times. So they'll fill in those dots and then they count the area, and that tells something about the amount of drug the person got. Well, this is sort of like the total exposure of CD4 count you get. It's very closely related to the mean, so it's not going to be necessarily that interesting as a different thing. But anyway, wanted to show how to do it just because people often consider it an interesting summary measurement. Just showing how you actually measure area under the curve. Typically, again, you don't have a measurement every second. You have it at certain points. They could be widely spaced and closely spaced, so you make little rectangles underneath the curve, and you add up those rectangles and triangles. That's how you do it. And if you want to figure it out, do it yourself. This is the code. By the way, this code's up on the website, so it's under Stata resources, do files. This all the code used to generate this is up there. You can see anyway, you're doing the same thing, and now I'm ranking them. I'm taking a systematic sample based on area under the curve. You do see a little bit of different thing because it's not exactly the same thing, and again, you're getting spacing things out, and you're able to see probably better the sort of characteristic patterns that you might observe in this data set. Again, just another way to do it. Oh, okay. Next lecture. No, I wanted that one. Yeah, okay. Okay, just continuing this, we're going to get more interesting kinds of things of processing the data in this lecture. So not just plotting the raw data, but actually sort of smoothing it in some ways to sort of get at patterns that you may not see if you just plot the raw data. Again, the idea is that there's some underlying patterns that may be obscured by the fact that there's lots of lability within an individual or just measurement error. So two sources of variability you can get over time. So the most obvious thing to do is to fit some model by individual. Now we are going to formalize this later by actual, so defining what essentially imply each individual has their own model, and we're interested in summaries of those models. So each person could have their own linear regression when it comes to CD4 count versus time, and I want to be able to fit simultaneously the parameters that define the sort of average. Now my thing. Okay, the average response across people, as well as the variation in that response. This is the first tangible. We're going to do it in a much more abstract way using these random effects mixed models, one of which you've already looked at, one that you will look at, that you looked at in lab last week. But here's a way of looking at it very tangibly. I can just do it. I can just fit a separate model by subject, and then I can characterize the distribution of the responses of CD4 count over time, for instance, or CD4 count versus viral load, whatever it happens to be. And this is a really useful thing to do when you're looking at particularly changes in time, because you can immediately get a sense of, okay, what are the variations, the kind of people I see in a very quick summary. So it's a great simplification of the data. It is a simplification. The true model is no doubt not linear. It didn't look linear on those plots, but it might be a useful way to try to get the kind of rate of change over time averaged over all their things. So so this is essentially what we're going to do. This again, if I, oops, I really should put here, that's a comma and a little I, because I'm not getting the marginal, that implies a different experiment than the one if I didn't have that I. If it didn't have that I, it would be if I have a big basket of outcomes, and or let's say balls. In each ball, there is a CD4 count and there is a time. And I could take a random sample of those balls and get the average CD4 count for the average for a particular time. I get among the balls, I get a set of times. Maybe some of them are ties. I can take just the mean of all CD4 counts that have a particular time, and I can report that as a model. But this, you can see here, I have these I's here, which tells you I'm not doing that. I'm taking all the observations on an individual, and I'm regressing their CD4 count versus their time. So I'm trying to derive estimates of these things. And again, it's very similar to the discussion we had earlier about getting the average of them. These things are going to be like random parameters. They're estimates of some parameter would be defined by having a infinite number of measurements on the individual. If I had thousands of measurements per individual because I had measurements every hour, I put those in, I got a linear regression, I could record the slope and the intercept for each of the individuals, and I would get I would get M intercepts, this case 483 intercepts and 483 slopes, and look at the distribution of those. I don't know what these are, so I have to estimate them, and I'm going to estimate them and then look at their distribution. That is not the same as looking at the distribution of the true ones, right? There is variation, no doubt. If I had that theoretical sample where I had an infinite number of measurements on an individual, there's no doubt variation in the true intercepts and true slopes, right? They're not all the same. Some people are going to go up a lot, some not so much. This has that variation in it, but it also has something else in it. So that variation I see, true variation among individuals, is confounded in this by what other source of variation? Say it louder. Sorry. Did you say measurement? Oh, actually, that's possible. Let's assume that the measurements are made accurately, but that's a good point. Could be measurement error. One more time? sampling variation within an individual. The fact is that these are made, if I took another random sample of different times, I'd get a different number. And this is one of the reasons, mixed models are so popular, is they're an attempt to separate out those two sources of variation with a model. You can separate out the true variance, the variance. There's the variance of beta 0I, and that is not, for instance, a coefficient. That is not equal. In fact, it's less than. So I can say it's less than or equal to the variance of beta 0I hat. Mixed models, random effects models, hierarchical models, multi-level models, all names for the same thing, try to attempt to get at this estimate with the model. They're able to subtract out the sampling variation. But of course, we're not doing that now. So you have to, when you look at the distribution of these things, it's not the real distribution of variability in slopes and intercepts. It's the variation of that plus the sampling variation, because we don't have a perfect estimate on an individual of their true intercept and true slope. So, but anyway, that's something to consider when this is done. You can, again, do this in many ways. This is an example of writing a little macro. It would be equivalent to a macro in SAS or a function in R. I want to write something that I can apply at the individual level. So I've defined a program called reg by ID here. And these things, Stata has the absolutely most inscrutable programming language. I mean, it's really quite good and flexible, but it's really, for me, just totally non-intuitive. So they have various ways that you can add these functions that allow you to add, different kinds of variables. You don't have to specify it's going to be CD4. It could be, I could do regressive, different y's versus different x. I want it to be absolutely general, and this is a way of doing that. This mark sample keeps track of if you do subsamples within this. There's all this kind of stuff here that is sort of inscrutable. But in the end, what it does is it gets estimates of the slope and intercept and stores them for that subject and puts them on that subject's line. So you can now apply this by ID and get slopes and intercepts by individuals. This, you can see the basic syntax. Now you could do other kinds of things here in this part here that you'd want to do. Maybe not slopes and intercepts. Maybe you want to get the variance of the residual variance after you do a regression. Whatever it happens to be. The basic structure will always be the same. You can use this as a template, but it's a very nice, powerful little tool to have in Stata, because you can now write your own programs, do your own things in a flexible way, and then implement them by ID. And so I've just given you an example of doing regression, and then in the end, it'll basically give me the intercepts and slopes, and it will also give me the predicted values. So I regress right here the variable list based on whatever subset I'm looking at. These commands here are very useful often, and the kind of the basis for these kinds of programs. Again, Stata has hidden things behind the scenes. So I run a regression. You've seen the output. Behind the scenes, it's storing things that as variables that you don't see in your variable list. You have to call them. You have to know what they're called. _b is the set of coefficients. It doesn't. It's not a variable in the sense that it's a column in your data set. It's a scalar or a vector. It's just a set of numbers that it keeps separate. People who are programmed and used to R don't have to worry about this, because R doesn't make you. R, you can have a data frame, which is the thing you typically operate in Stata, and you can have lists, and you can have vectors, and you can have functions. You can all part of the same data set. It's you can list them. It's easy to see. These other programs like SAS and Stata, since they're not really written for programmers, they're written for users, don't make this terribly easy. So they have these hidden things behind the scenes that you have to go find, and then you can find them in the manuals and how to do it. It's not a huge burden, but they're there. That's how they make the output from a Stata. They do these, it's doing least squares. That's a matrix multiplication. It's storing these results, storing the variance covariance matrix so it get the standard errors, and keeping them as hidden kinds of variables behind the scenes. Now I'm just grabbing them, and now which is what these things, after I've made such a mess, that's what these things are. That's a variable slope, which is now going to be a variable, and it's going to give me the slope for that person's thing. And anyway, that's for those that are ambitious about stata, and want to use it for things that go beyond the standard regression stuff. These are really valuable little tools to learn. So I've done that. I've done regression by ID. That's all. After I wrote all that code, I just have to run that now. Quietly is not a necessary term. It just says don't give me, if like every time it does a regression, there's a warning or something. It just says don't write it to my screen. I don't want to know. And then by ID, it does each regression, and then it's storing those in that new variable slope and intercept, and also the predicted values. So once I run this, I'm going to have new columns in my data set, new variables that I can now display and give me summaries of the patterns I see based on this linear regression. I'm just giving an example by just taking a set of 2 IDs and plotting it. So once I do that, you can see what I get. I just took 2, not really random. I just took 1 and 3, and I get back this predicted value. I'm just plotting their data, and of course, static plot commands allow you to plot raw data and then overlay it anything else you want to plot on it, like the lines. So this comes from the program I just ran, and this comes from the program. So I've got now these 2 slopes. And now the question is, how can I use that to make summary plots of all the individuals? Well, the first thing that is sort of interesting to do is just look at the distribution of slopes and intercepts. These slopes and intercepts have a meaning here. If you take the model seriously, what is the intercept? This is actually kind of an interesting, because it brings up a whole interesting point about how you should estimate things. What's a better estimate for this value? What is the intercept defined as in this case for each individual? Remember, it's the regression of CD4 count versus time. So the intercept is at the start when they enter the study. So it actually has a meaning. What would be better? To take the intercept, let's say I have 2 choices. I have their CD4 measurement at time 0, and I fit this line and get the intercept at time 0. How are those different? They're both essentially estimates of the same thing, the CD4 count at time 0. What's different about them, and what might be better and what might be worse? What is the 2 things that influence, the 2 sources of error that influence both of those? So first of all, taking the most people, I do have the observation at time 0. They come and I get it, right? So I give 1 observation. So what's the virtue of using that as my estimate of where they start? One more out loud? Sorry. Yes, observed it. I didn't make any assumptions, right? No assumptions. There's no assumptions at all. That's a completely non-parametric way of estimating it. I'm not adding bias by assuming that there's a line. What's the pitfall? I only have 1, right? It's usually an estimate of something from 1 is not very good. It could be that I measure things immaculately. There's no measurement error. It depends on really how I envision that thing I'm getting at. Is there lots of layability over time that is noise? I can think of it as random error, and therefore that time at 0 represents what's sort of the characteristic value plus that error, or is it really just the accurate measurement of that subject? It's really how you think of the observation, sort of. But the first case, I have no bias, but it's highly variable, right? Because let's assume there's just measurement error. I could take another measurement the same day and got a completely different value, which is true in this case. CD4 count has lots of measured. So there's lots of variance, but there's no bias. In repeated experiments, the kind I take that first value, that mean of that is the thing I want. In the other case, what is the virtue of taking the intercept? I'm using all the data, right? So I'm intercept's basically borrowing across getting this observation here at time 0 is borrowing across the whole data set. It can borrow across it because I'm assuming a model. That's what models smoothing allows you to do. It allows you to borrow information across all your data. So I'm getting an estimate here that isn't just a function of whatever value I have here, or let's say close to here. It's a function of all the data. And the models, of course, because they assume that I can sort of extrapolate from one point to the other by assuming this model allows me to borrow data across the whole data set. So I'm going to get an estimate here that has much lower variability. It's much, it's really like an average of a lot of things as opposed to an average of one. What is the downside? Of course, if the model's not true, then it's biased, right? I mean, it could be the truth looks like something like this. And if I fit a line there, I'm going to get that's maybe the true value, and I'm going to get that. So that'd be terrible estimate if the model's bad. So I mean, this just always comes up in statistical estimation, where models are great because they borrow information and they reduce variance, and we're going to talk a lot about them. The downside is, of course, that if it's wrong, they're misleading. They introduce bias. So here's a nice, simple little example of that. Okay, all I'm doing here is now taking those estimated slopes and intercepts at the individual level and plotting them. So let's look at the slopes first. What gestalt do you get here? This just gives the number of people who are in each group. Here's 0. These slopes here are positive, meaning over time CD4 count is increasing. These are negative, meaning they're decreasing. So what's your general gestalt from that plot? This is a nice summary of sort of average rates of change with CD4 count after introduction of heart. Exactly. That's most people here are very, very, or close to 0. 0.5, the unit is day. So in essence, that's not, you have to think of a unit of time that's more meaningful. Let's say a month. So 30 days, 30 times 0.5 would be 15, right? So this would be an increase up in this higher end, people, if the slope is representing their true rate of change, are increasing 15 CD4 units per month. That's not very big. That's pretty small, but I mean, and then, of course, there's one person that's way out here. Now, I don't know if it represents 2 observations that just happen to be very, because the person wasn't measured often. You'd, of course, have to look. That's the problem with these plots, is because that sampling variability and the variability that's the true variability is confounded in the same plot. So most positive, so there is a positive. It's relatively small, it looks like, for most people, close to 0. And then there is a few people that are going negative, and that's probably because they're beyond, given this particular kind of treatment available at the time, they're probably beyond being able to be saved by the heart. Okay, I'm just doing the same thing here, where I now can. I'm just ranking. I'm not using the plot the slopes and intercepts to actually plot them. I'm just using them to rank them. So I'm taking now all the slopes, and I'm systematically going from the lowest slope to the highest slope, and this is the range of values I get. So it's just another way of systematically sampling the data, and now sampling not with regard to the mean, which is kind of like, in some ways, a little bit more like the intercept. It's more like what happens to their rate of change Obviously, this person's on the higher rate of change, and there's people on the lower rate of change. They're going to be going down like this. But I can do other things that actually use the model I fit by plotting, in fact, the range of slopes, the range of lines I get. This is just taking a random sample of those lines. I'm sorry, not a random sample, systematic sample. And you can see exactly what we saw in that you get most people are pretty flat, or there is an increase more than there is a decrease, and there are a few decreases. So this is basically, it gives you kind of a nice gestalt for what's happening among that group of patients if you really wanted to report and say how, let me close that quickly. Okay. This sort of takes, in some sense, a lot of the noise out and gives you at least an average kind of response over time. It gives you a really nice gestalt. You can see, some people, of course, are flat, starting low, and most likely dying very quickly. Some people are starting low and responding quite well. Some of the steeper slopes are, in fact, ones that started low. But for the most part, they're pretty flat. Okay, I'm just going to introduce this, and then we'll stop for the day. So that is one. Models are a form of smoothing, just for the reason I said earlier, that they're borrowing information across the data set to try to get an estimate of, let's say, the mean at a particular time or a particular combination of covariates. And you can employ different levels of smoothness. Parametric models are the most smooth. I mean, if I go back, what's the smoothest model I could fit? That is borrows the most data for a single parameter. Well, I could just fit a flat. That's just the mean, right? I could just take the grand average over all the data, and that would be a very, very smooth model. It would assume that everybody has the same CD4 count on every time. So I get to borrow a lot of information. That's great. I get to borrow all 483 times the number of measurements per subject to get an estimate. That's going to be an estimate measured with very little variability. But the problem is, of course, the actual trends that you get. So the next form, of course, that I showed was the line that you see there, and that's probably as second smooth as you can get. I'm not assuming that it's flat, but I'm assuming that it has to be either a slope up or a slope down. So in this case, it's I'm not allowing any curves, which would borrow less data. I'm still requiring a fairly strong model, and that model allows me to borrow lots of information across the data set, but it adds more bias because it's a bigger assumption. So there's something kind of in between. And then on the extreme end, what could I have done? That's this. At the extreme end, I just plot the points, right? That's assuming nothing. There is no model there. I'm just plotting the points. So that would be, considered non-parametric, because in fact, that's also got to be terrible because there's all kinds of noise. And these things probably are not necessarily real. And if I'm doing that, I'm getting an estimate that's, it's not biased, but it's obscuring maybe some pattern because of the noise I'm failing to smooth through. Now, in between doing absolutely nothing and doing something that's really, really a strong assumption, like a constant mean or a linear model, is general terms called smoothing. I just want to point out that parametric models are smoothing. They just aren't called that, but they are a form of smoothing. But you can do things that are sort of what are called semi-parametric smooths, in that they don't really assume a model, but they borrow information across the data. So it's a compromise between doing nothing and doing too much. It's kind of doing just the right amount. There are many kinds of ways of smoothing. They all have this kind of similar heuristic to explain them. So if you can learn, kernel density smoothing is one of the most common, really, kind of smoothing. And all forms of kernel density smoothing have really, or kernel smooths on scatter plots have the same sort of heuristic explanation for what they're doing. They really are they really are explicitly a compromise between fitting a parametric model and fitting no model at all. They're like fitting a parametric model, but only over a little portion of the data. That's essentially what they do. They fit like a little model over a little portion of the data. And they really can be thought of as a series of little weighted averages as you move along. Or little weighted lines as you move along. And we'll explain that in a sec. You know what I'm doing? I'm just gonna talk about it here quickly, and then we're gonna stop. So basically, this assumes nothing here, right? Let's just look at this one here. I'm just connecting the dots. But what I could have done is I could have gone right here, and I could have said, okay, as opposed to just connecting the dots, at this point here, I'm just going to take the average of all these observations here. So I smooth, but I smooth very locally. I just smooth a little bit. I just borrow a little bit of information. I don't borrow it over the entire data set, which would be assuming essentially just a single flat line. And I don't borrow like a linear regression. I just say, okay, I want to borrow, but I only want to borrow locally. And I'm not going to borrow beyond that. So I do that. Now, again, I could take the average. I could fit a little line like that. There's various different ways of doing that. The little line is called Loess smoothing, but they all have that similar property that you're fitting some kind of little parametric regression, but not over the whole data set, just a point there. And then I could go over here and do another one, another little line, and fit it there. And I can do another one here. And then at the end, I just connect them. You don't get back a formula. All you get back is a plot, essentially. You just get back where you go across in a grid doing these little local little models, and then at each grid point, you predict what the model is telling you would be if I only use that little data there, and I connect those dots, and that is a smooth. These are the ways of getting a pattern in your data that smooths out what you hope is the noise without assuming any particular model, because I'm not assuming how this point here goes to this point here. It could go up, it could go down. There's no formula that specifies a parametric model. And the amount of smoothing I get is a function of how wide I look. And we'll talk a little about that next time. I can look in a really, really, really narrow interval, and therefore I'm not borrowing much information at all, and therefore my plot will look rougher when I connect the dots, because as I go from here to here, I'm using completely different data. So there's nothing to connect them. There's nothing to smooth across it. It's the data that's shared in the estimation process when I go to point that makes it smoother. The more data is shared, the smoother it is. If I'm taking just a simple average, I have a lot of observations that are overlapping, contributing to the average. That means it's not going to change much, right? It's quite smooth. At the limit, if I get very, very small, I'll just get back eventually to the point that I'm connecting the dots again. So you can see in the limit, if I make it smaller and smaller, I'm just going to go back to nothing, assuming nothing. If I use the neighborhood as the entire data set, I'll just either get a flat or a line, depending on what I'm doing in this little space here, whether I'm fitting a line or just taking the average. But so in that limit on both sides is called the bandwidth. Smaller bandwidth, really you can just think of it the size over which you're taking that average, how much of the x-axis you're using locally guides the smoothness, and it's the kind of parameter you set. We're not going to go into like selecting optimal bandwidths and things like that. There's whole courses that deal with things like smoothing. But we'll give you some idea about how to do it. And it's an incredibly effective tool for longitudinal data because it can really get rid of a lot of sort of noise and give patterns, but it doesn't necessarily impose any form. So you can see, in fact, if what you really want is something that might plateau and go flat, or lines are good fits, because, in fact, when you assume nothing, you still get a line, etc. So next session, we'll finish that up.